In section 3.5, we'll talk about finding the derivatives for the trigonometric functions. So we'll start with derivatives for sine and cosine, and then we'll move on to secant and cosecant and tangent and cotangent. And then we'll talk about higher order derivatives and look for patterns with the derivatives for sine and cosine. So rather than do a formal proof of the derivative for cosine, what I want us to do is just take a look at a plot of a function that we would derive from just thinking about the difference quotient. So if we were to find the official derivative, the long way, we would look at the limit as h goes to 0, cosine of x plus h minus cosine of x over h. But what I want us to do is just pick a specific arbitrarily small value of h or value of h that's close to 0 and look at that graph. So we're going to look at cosine of x plus 0.001, right? So that would be our h value, minus cosine of x divided by that same h value, 0.001 again. Right, so we're just picking a specific value of h that's close to 0 and looking at this graph. So grab your calculator or GeoGebra and plot this curve. And let's take a look and see what we think it seems to look like. Actually, I have this already set. So here's what I have for cosine of x plus 0.001 minus cosine of x divided by 0.001. It's showing up as this graph. And what you can notice is I don't have the tick marks at fractions of pi, but you can see that at about negative pi, this crosses the x-axis, and about pi, this crosses the x-axis. It goes up to 1 and down to -1. This sure acts a lot like the graph of sine, except that it's upside down, right? It has a period of pi, the range is -1 to 1, it goes through 0, 0, and pi, 0, and negative pi, 0, but it's reflected over the x-axis. So, based on our graph, we would say it looks like the derivative for cosine, which this graph should be approximately the same as. We would say it looks like the derivative of cosine of x would be the opposite of sine of x. And that is correct. So again, we're not going to go through a formal proof, but based on this graph, we would say it sure looks like the derivative would be the opposite of sine x, and that's exactly what it is. So we just kind of investigated the derivative for cosine, which is the opposite of sine of x. The derivative for sine is cosine without the opposite sign. This pattern of the derivatives for co-functions being negative is going to extend to the others. So that will help you remember. So the derivative for sine is cosine. The derivative for cosine is the opposite of sine. So if we're taking the derivative of a trig function that starts with co, there's going to be a negative sign involved. Okay, so now example 1, we want to use these two that we just wrote down to figure out the derivative for a quotient that involves them. So this function is 3 sine x over x squared plus cosine x. And we can say, oh, we're going to need the quotient rule because I have a quotient. So the derivative for f, I want low d high minus high d low divided by low squared. Right, and let's just put those pieces together here. Low is x squared plus cosine x. D high would be 3 times the derivative of sine x, so 3 times cosine x. And then we want to subtract high, d low, And the denominator, low, is the sum of two terms. So I want the derivative of the first term plus the derivative of the second term. The derivative of the second term would be negative sine x, so I'm going to write minus sine x. And then divided by low squared, so divided by x squared plus cosine x squared. And be very careful, you don't want to reduce the factor that has x squared plus cosine x in the numerator and the x squared plus cosine x in the denominator, because the numerator doesn't, like, not both, both terms in the numerator would need to have that same factor, and they don't both share that factor. So we can't reduce this. We could just leave it just like it is, and that's just fine. Example 2 asks us to find the derivative of the g of x equals x squared times sine x times cosine x. And so here we'll need the product rule, but we want to pay attention to the fact that we have three factors. So we need almost an extended product rule. When we have three factors and a product rule, it helps to group two of them together and treat them as two factors at the start. So maybe I'll keep x squared by itself, and I'll think of this as x squared times the second factor, sine x cosine x. And so when I do my derivative, I'll think the derivative of g is going to be the first factor, and I'm just going to map it out. So times the derivative of sine x cosine x. So I'm not actually taking the derivative, I'm just writing my plan down right now. So first times the derivative of the second plus the second factor times the derivative of the first. So I've got this plan sketched out. The derivative of sine x cosine x will also involve the product rule. So we will have x squared times, and then we'll do the product rule again inside here. So we would say the first times the derivative of the second, which will now be the derivative of cosine. The derivative of cosine is negative sine x plus the second times the derivative of the first. Derivative for sine is cosine. So the orange and green here would represent the derivative of sine x times cosine x. Then we move on to plus sine of x times cosine of x times the derivative of x squared, which is just 2x. So it's fine to leave it just like that. If you want to, you can distribute the x squared in that first group. We could say this is maybe negative x squared times sine of x squared plus x squared times cosine of x squared. And then plus 2x times sine x times cosine x. Every once in a while, I'll see someone try to distribute that, the 2x right here. That's not a distribution because we don't have an addition that we're multiplying over. It's just, we're just multiplying those three factors together. So just like this, 2x times sine x times cosine x for that last term. All right, then let's look at an application. A particle moves along a coordinate axis, or a straight line. Its position at time t is given by s of t equals square root of 3t plus 2 cosine t, at least for t between 0 and 2 pi. And we want to know at what times is the particle at rest. right? And at rest would tell us something about the velocity. If it's at rest, the velocity would be 0. So we want to know what are the times when the velocity of this particle is 0. So we need to figure out what the velocity is, and we remember that the velocity is the first derivative of position. And the first term in this position function is just linear. The square root is just on the 3, not on the t. So that will be square root of 3, the slope of that linear function, the coefficient on t, plus 2 times the derivative for cosine of t, which I'm going to rewrite here, which is going to be a negative. So let's write down minus 2 times sine t. So there's our velocity, and we would say the velocity is 0 if and only if square root of 3 minus 2 sine t is 0. So that leaves us with a trig equation to solve. We want to isolate sine of t. So square root of 3 would be 2 sine of t, which means sine of t would be square root of 3 over 2. So you want to think about the unit circle and think about where sine of t is positive. Sine is the y-coordinate of the point on the unit circle. So quadrant 1 and quadrant 2 would be the quadrants for a positive sine value. And if the sine value is square root of 3 over 2, remember that's the angle of our familiar angles that's closer to the y-axis. So that's going to be pi over 3 in quadrant 1 and 2 pi over 3 in quadrant 2. Right, because our points would be x-coordinate 1/2, y-coordinate square root of 3 over 2, and x-coordinate negative 1/2, y-coordinate square root of 3 over 2. So we would say t equals, and t, remember, is the angle, pi over 3, or t equals 2 pi over 3. So those are the times when the particle is at rest. Then we'll take a look at the derivatives for the remaining standard trig functions. So cotangent, secant are the two we'll look at, and then we will recognize, after we develop these two using the quotient rule, then we'll just write down the derivatives for the other two. Okay, so let's find the derivative for cotangent, recognizing that cotangent is just the ratio of cosine of x. Let's be more careful here. Cosine of x over sine of x. So I want the derivative of cosine of x over sine of x. And this would require the quotient rule. So we want, again, low d high minus high d low over low squared. So low is sine of x. D high would be negative cosine of x. We want minus high is cosine of x. D low would also be cosine of x. And low squared is sine of x squared. And looking at this, I can see I made an error on the derivative of the numerator. I was going too quickly, or maybe it's too early in the morning. So low d high should have been negative sine of x, not negative cosine of x. That looks better. So low d high minus high d low divided by low squared. And now in the numerator, I can see I have negative sine of x squared minus cosine of x squared. And that's starting to look like a familiar Pythagorean identity if I factor out negative 1. And then I can see, oh, sine of x squared plus cosine of x squared, that's just 1. So this will give me -1, excuse me, over sine of x squared. And that is the same as the opposite of cosecant of x squared. So remember with trig functions, we write the square like next to the function, but remember this means the same thing as -1 times the function cosecant of x. Cosecant of x, look at it right here, squared. That's the same thing. And sometimes it's helpful to rewrite it that way, even though conventionally we would write the power next to the trig function. All right, and then the derivative for secant, we would say, okay, secant is 1 over cosine of x. And even though the numerator is really simple here, this also requires the quotient rule. So the derivative for cosine will do low d high minus high d low again. So low is cosine. D high would be 0 minus high. D low is negative sine of x. And that is divided by low squared. So cosine of x squared. So let's simplify this so we can have a nicer formula for it. Let's see, so we have 0 when we multiply those two factors together, and then plus sine of x. So I'm just going to write this as sine of x over cosine of x squared. And just because it'll help us see how we can rewrite this, I'm going to write cosine of x squared as cosine of x times cosine of x. So that's going to give me sine of x over cosine of x times 1 over cosine of x if I separate those two factors. And I can see that as tangent of x times secant of x. And for whatever reason, it's much more conventional to put them in this order, secant of x times tangent of x, for the derivative for secant. So 2 of these we've established using the quotient rule and relating them to sine and cosine. Let's write down the 6 derivatives for these trig functions. So sine is cosine. Cosine of x, its derivative is opposite of sine of x. The derivative for tangent, we didn't establish. We established the derivative for cotangent. Cotangent was the opposite of cosecant of x squared. And we found the derivative for secant was secant of x tangent of x. The derivative for tangent is secant of x squared. And the derivative for cosecant is the opposite of cosecant of x, cotangent of x. And these you just need to memorize. They come up frequently enough that you do not want to need to go through the quotient rule every time you need the derivative for tangent or cotangent or secant or cosecant. But notice some patterns here. Like I mentioned earlier, the derivatives of co-functions have a negative sign. And this also seems to be sometimes helpful for people. If you look at this set of letters, this can help us with the derivatives for secant and tangent. if I go this direction, starting with the secant, I have the derivative for secant. Because I say the derivative of secant is secant times tangent. And if I go the other direction, starting at the t, I have the derivative of tangent. The derivative of tangent is, so the derivative of tangent is secant times secant, or secant squared. Right? And the p is there to remind you that those are positive. And then we can kind of get the derivatives for the others, for cotangent and cosecant. Cotangent is negative, so not positive. Cosecant times cosecant. And the derivative for cosecant is negative, not positive. Cosecant times cotangent. So this PSST can help you with the derivatives for secant and tangent, and if you put cos on them and negative, then you have the derivatives for cosecant and cotangent as well. All right, so example 6 here, we want to find the derivative for f of x equals x minus tangent x over 3 secant of x. So we'll eventually have these memorized, but we would still need to use the quotient rule because now we have a quotient of these trig functions. So we want low d high minus high d low over low squared. So f prime will have low is 3 secant of x. D high will be the derivative of x, which is just 1, minus the derivative for tangent. And we know that's going to be positive. Starting with tangent, we'll have secant times secant. And then we want minus high d low. So we'll have 3 times the derivative of secant. Secant derivative is secant times tangent. And then we have divided by low squared. All right, this one we can probably clean up a little bit because I can see there's actually a factor of 3 secant x in both terms of the numerator. So if I rewrite this, I could notice there's a 3 secant x right here in this first term, and there's a 3 secant x right there in that second term, and I have a factor of 3 secant x in the denominator. So it's fine to factor that out of the numerator. And then I would have 1 minus secant of x squared minus x minus tangent of x times tangent of x over 3 secant of x times 3 secant of x. And then I can reduce these two. And then I'm noticing that I feel like I have some, maybe potentially a trig identity in the numerator that I could clean up a little bit. So let's keep going with that. So we have 1 minus secant of x squared minus x times tangent of x, because I'm distributing this tangent here. And then it looks like I would have plus tangent of x squared. And if you're like me, you might not remember exactly how the trig identity with secant of x squared and tangent of x squared looks, but I know I can establish it because I know I can remember this one. And if I want to get to something involving secant and tangent, I would look at this one and say, I better divide by cosine of x squared. That's going to create secant of x squared, and this will create tangent of x squared. So if I start with the identity I know, and then divide everything by cosine of x squared, I will establish for myself the one that I can't always remember. Right? And so I say, all right, I actually see that I have a 1 plus tangent of x squared. So I could take those two and rewrite that as secant of x squared. And then I have a secant of x squared minus a secant of x squared. So those can be reduced or added to make 0. And I can simplify this all the way to x tangent of x over 3 times secant of x. And that's pretty well simplified, but then I'm also thinking, I bet I could get even better because tangent is sine over cosine and secant is 1 over cosine. So I'm just going to keep going with this just for the practice with rewriting trig stuff. So sine of x over cosine of x. And then this would be over 3 over cosine of x. Right, so I've got, there's my numerator, and here's my denominator, and now I could multiply by the reciprocal of the denominator. And I can see then those will cancel, and so what I really have is x times sine of x over 3 for the derivative. So much simpler than what we started with, right? And again, if our goal is just to find the derivative, it's fine to leave it in a complicated form, but oftentimes we're going to maybe want to know, well, where is there a horizontal tangent line, or where is the derivative equal to square root of 3 over 2? And then we would need to work with this until we can get it cleaned up a little bit. In example 7, we're trying to find the equation of a tangent line to a graph of a given function at a given point. So remember that the equation of the tangent line, the structure that we want is y is the slope, which is the derivative at the given point, times x minus the x coordinate at the given point. So in this case, x plus pi over 4, since our x value is negative pi over 4, plus the function value at that anchor point, so f of negative pi over 4. So the pieces we need to find to finish this are the derivative and the function value. So the function is given, let's start there. The function at negative pi over 4 will be 2 times negative pi over 4 plus cosecant of negative pi over 4. Cosecant is the reciprocal of sine. Sine of negative pi over 4, down here in quadrant 4, that point on the unit circle would be square root of 2 over 2, negative square root of 2 over 2. So the sine value is negative square root of 2 over 2. The reciprocal of that would be 2 over negative square root of 2. And that simplifies to negative square root of 2. So if we clean this up a little bit, we'll have negative pi over 2 minus square root of 2 for the function value. And then for the derivative, first, before I plug in a value, I need to find the derivative at any value of x. So we'll have the derivative of 2x, which is just 2, plus the derivative of cosecant. Cosecant, that starts with a co, so I know it's going to be a negative. And it's negative cosecant of x times cotangent of x. So we want for our slope, we'll fill in the value negative pi over 4 for x. We'll have 2 minus, we just computed cosecant of negative pi over 4. So what we got when we did that was negative square root of 2. And we want to multiply that with cotangent of pi over 4. Cotangent is the ratio of the x-coordinate to the y-coordinate. The x and y coordinate at that point on the unit circle are the same absolute value, but they have opposite signs. So when I take the ratio of x to y, I'm just going to get negative 1. So it looks like I have 2, and then I've got, it's going to be subtraction because I have 3 negative signs multiplied together. So 2 minus square root of 2 for this slope. So the equation of my tangent line is going to be y equals, the slope is 2 minus the square root of 2, and then I want times x plus pi over 4, and then that's, we want to add the function value, which was negative pi over 2 minus square root of 2. We could probably clean that up a bit. Let's work on that. I'm just seeing it looks like a pi over 2 and a negative pi over 2 that might cancel out. So let's do this. If I'm going to leave 2 minus square root of 2 times x, because that's going to be the slope. So the slope times x. And then I'm going to distribute this 2 minus square root of 2. I'm going to multiply that with the pi over 4. And that's going to give me plus 2 pi over 4, which is pi over 2, minus square root of 2 pi over 4, minus pi over 2, minus square root of 2. And so it's not that much cleaner, but I can see I have a plus pi over 2 and a minus pi over 2. So I could rewrite this as y equals 2 minus square root of 2 times x, and then minus square root of 2 pi over 4 minus square root of 2. That's a little cleaner, I guess. Either one of those would be perfectly fine on a quiz or a test. All right, example 8, we want to find the points at which this function has a horizontal tangent line. And remember, horizontal tangent line means the slope of the tangent line is 0. And that means the derivative is 0 because the derivative represents the slope of the tangent line. So we want to find the places where the derivative is 0. And our derivative is 2 plus square root of 3 times cosine x. And so we want to know, where is that 0? And that is going to be 0 if and only if 2 plus square root of 3 times cosine of x is 0. And I want to isolate cosine here. We had a very similar problem earlier in this section, didn't we? But let's keep going here. So we have square root of 3 times cosine of x equals negative 2. And that would give us cosine of x equals negative 2 over the square root of 3. And this is telling me that this is not a good problem because that's not a familiar cosine value. I think what we need to do here is change the order of these coefficients. So let's make the square root of 3 the coefficient on the x and the 2 the coefficient on sine. So sorry to have to restart that, but updated function. f of x instead will be square root of 3x plus 2 sine of x. And then our derivative will be square root of 3 plus 2 times cosine of x. And the derivative will be 0 if and only if the square root of 3 plus 2 cosine of x is 0. And then we want to isolate cosine. So we'll have 2 cosine of x is negative square root of 3, and cosine of x is negative square root of 3 over 2. Okay, so now we have something we can solve. And if we think about the unit circle, cosine of x is negative in quadrants 2 and 3, because the cosine is the x-coordinate on the unit circle. So we want the angle where we have the cosine value negative square root of 3 over 2. And if the x-coordinate is negative square root of 3 over 2, that's going to involve a pi over 6. We would have 5 pi over 6 or 7 pi over 6. And it said determine the points, which would imply we want both an x-coordinate and a y-coordinate. So we set the derivative equal to 0 because we wanted a horizontal tangent line. We found the x-coordinates where that slope is 0, but now we want the y-coordinates, and those always come from the original function. So the points will be 5 pi over 6, f of 5 pi over 6, and 7 pi over 6, f of 7 pi over 6. So that's going to be 5 pi over 6, and then our updated function here, square root of 3 times 5 pi over 6. It's kind of a strange looking number, but that's exactly what it would be. So square root of 3 times 5 pi over 6 plus 2 times sine of 5 pi over 6. If we think about the coordinate here, we'd have the x is negative square root of 3 over 2, and the y is a half. And down here, when x is 7 pi over 6, I would have negative square root of 3 over 2 and negative a half. So sine of 5 pi over 6 will be a half. So plus 2 times a half for that one. And then when x is 7 pi over 6, we'll have, let's see, square root of 3 times 7 pi over 6 plus 2 times sine of 7 pi over 6, which was negative a half. So we can rewrite this one as 1 and this one as negative 1. And that would be our simplified form. So 2 points where we have a horizontal tangent line, x equals 5 pi over 6 and x equals 7 pi over 6, and then we find the y-coordinates that go with those. The next thing we're going to do is take a look at a pattern that we see when we look at higher order derivatives for sine and cosine. So let's start with y equals, or f of x equals sine of x. And let's just start looking at the derivatives for sine. So f prime would be cosine of x. F double prime will be the opposite of sine of x. The third derivative will be a factor of negative 1 because there's a scalar multiple here of negative 1, but then back to cosine of x. And then the fourth derivative is going to be back to sine of x. And now we can see we're just in this 4 function cycle, right? We'll see this repeat every fourth derivative is going to match, right? So you can kind of see it like this. I've got sine x, and that's going to go to cosine x, and then it's going to go to negative sine x, and then to negative cosine x, and then it's going to go back to sine, right? So every fourth derivative, every eighth derivative, every 12th derivative is going to be back to sine, and they will cycle in this circle, right? If I start with g of x equals cosine of x, then g prime will be negative sine of x. G double prime will be negative cosine of x. The third derivative will be sine of x, because we would have the opposite of negative sine of x. And then the fourth derivative will be cosine of x again. And this will just repeat in that same cycle. So what you can see is this circle is going to be the same circle no matter where we start. If I start at sine of x, I'll get back to sine of x every 4 derivatives. If I start at cosine x, I'm still going to go in this same order, but then every 4th, 8th, 12th, and so on derivative will be cosine. Right? So it's a cyclical derivative pattern. So let's see, if I want the 23rd derivative of sine, I could think, well, if I can get to a multiple of 4 that's close to 23, then I can figure it out pretty quickly. So I would know the 20th derivative of sine of x is just sine of x, right? Because the 4th derivative, the 8th derivative, the 12th derivative, and so on, every multiple of 4, I'll be back to sine. So the 20th derivative is going to be right here. So 21 would be here, 22 would be here, and 23 would be at negative cosine of x. Right, so I can use the multiple of 4 that's closest to 23, and then work my way up from there. Or I should have said closest but less than, but even I could also go closest but greater than. So 24, I could also have used, well, the 24th derivative of sine of x is going to be sine of x. And then I would have said, well, 24th is right here, so 23rd would be the one before it. That works too. And let's do the same kind of thing, but now let's look at one with cosine. So if I want the 34th derivative of cosine, I would think, well, 34 derivatives, the 32nd one would be the one that's the closest multiple of 4, that's less than 34. And the 32nd derivative of cosine then is going to be cosine of x. So back on my picture here, I'm thinking here's 32, and then I want 33 would be here, and 34 would be there. So I would have negative cosine of x. Right. So if you can just establish this cycle for 4 of them, then you can use that pattern to find any of them. All right, then example 10 says a block attached to a spring is moving vertically. Its position at time t is given by s of t equals 2 sine t, and we want to find the velocity and acceleration when t equals 5 pi over 6, and then compare the values and decide whether the block is speeding up or slowing down. So we have s of t given. We can use that to find the velocity, which is just the first derivative of position. and the acceleration, which is the second derivative position or the first derivative of velocity. So we have those three functions all set. We're asked to find velocity and acceleration at a specific time. V of 5 pi over 6 would be 2 times cosine of 5 pi over 6. And thinking about our unit circle, 5 pi over 6 is over here in quadrant 2. And the cosine value there is negative square root of 3 over 2. So this will be 2 times negative square root of 3 over 2. So negative square root of 3. And we don't have units, but at least we can see that this negative sign means that it's moving downward, since it said it was moving vertically, and we would assume that up is the positive direction. So moving downward, so this might be something like negative square root of 3 inches per second or something like that. Okay? And then let's look at acceleration at 5 pi over 6. And that is negative 2 times sine of 5 pi over 6. Sine of 5 pi over 6 would be a half, right? Our coordinates on the unit circle there are negative square root of 3 over 2 and a half. So negative 2 times a half. So we'd have negative 1 for the acceleration, right? And we're asked to compare these two values and decide whether the block is speeding up or slowing down. And you will recall from the previous section that when the signs of v of t and a of t agree, the object is speeding up. So in this case, we see that both of them, the sign for velocity and the sign for acceleration, are negative. So this spring right now is speeding up, or the block is speeding up. Right. Since A is negative, we can think that that tells us V is decreasing. But if V is already negative and it's decreasing, it's moving to a number that's further from 0, right? So it's moving in the negative direction at a faster rate. So that's, I would say, this object is speeding up. Let's take a look at the graph, and that will help us kind of understand why this makes sense. So if you look at the graph of 2 sine t, or 2 sine of x, I'll type in. Right, at 5 pi over 6, we are somewhere between pi over 2 and pi, right? And you can see the block is moving downward, and it's going to be moving fastest right as I cross pi. So it's increasing in speed, and then it starts to slow down and move a little less quickly, still in the negative direction, until we get out to 3 pi over 2. But you can see you're like right in this area, a little bit left of pi, past pi over 2, so in the area of 5 pi over 6, the block is speeding up and moving downward.